Alright, so section 6.3 is on continuing with the idea of functions and a specific type of function called square root functions, and you've probably seen these before. We want to do two basic things. First of all, talk about how to graph them, and then secondly, how to use the graph or the equation to find the domain and the range. The domain refers to what x could equal, and the range refers to what y could equal. Okay, so here's just a basic picture of in the general term for these are called radical functions. That this sign right here, that's called a radical or a root sign. Radical comes from the Latin word for root, radice, which means root in Latin. So it looks basically like this. This right here is the parent function. And if you want to see why this makes sense, let's think about it. If y equals the square root of x, and I started plugging values in for x, I'd have to ask myself, what values could I not put under the root? And obviously you can't take the square root of negative numbers. Those are not real. So that's why the domain of this graph means x has to be anything that is greater than or equal to 0. Because you can't take the square root of something that's less than 0. Like the square root of negative 1, that's not a real number. So you can start at 0. The square root of 0 is 0. So that's this point. The square root of 1 is 1. So let's say that's this point right here. Okay, then usually for x, the easiest numbers to put in this table would be the ones that you see me putting right here, because those are perfect squares. So the square root of 4 is going in here for x. The square root of 4 is 2. So 4, 2 would be, let's say, about right here. The square root of 9 is 3, and so on. So you can see this curve just kind of rises very gradually. The domain, like we said, is x is greater than or equal to 0, and you can see the range refers to the fact that y can never go below 0. That thing I just circled, y never goes below there, so that's what this means. The range of the square root function are only positive y's, because you're only going to get positive numbers when you take square roots. Okay, the end behavior, it doesn't have end behavior as x goes to negative infinity, because on this side of the graph, x doesn't go here, x doesn't go to negative. But as x goes to positive infinity, as we're going this way, you can see that this curve is very slowly rising up. And if you went further enough, it would eventually wind up at positive infinity. So that's what the basic function looks like. This is just a humorous cartoon. Sometimes people like to ask, when am I ever going to need to know square root functions in real life? So this person came up with a stop sign, or the speed limit, which is put in terms of radicals. So obviously if you don't know what a radical is, you're not going to know what speed limit to drive. So kind of a humorous way to answer that question. Alright, it says identify the domain and the range. Well, really all we need to do is we need to know this. We need to know that this thing cannot be, this thing here cannot be negative. Okay, it can't equal a negative number. So what's the dividing line between negative and positive? 0 is the dividing line. So to find the domain, what we do is we set the thing under the square root, set this thing equal to 0. And then we see what value would cause that thing to go negative. So if we solve this for x, we would get x equals negative 4. So what does that mean? That means if x were less than negative 4, this thing right here would turn out to be negative. Like if you plugged in negative 5 right there, you get negative 5 plus 4. That's negative 1. You can't do that. So x has to be greater than or equal to negative 4. Why is that the domain? Because again, if x is anything that's not greater than negative 4, anything that's less than negative 4, you'll get a negative underneath there. Okay, what about the range? Well, the range is still the same. If you remember this parent function that we just talked about, it looks like this right here. Okay, the range, we didn't do anything in this graph to the range. We didn't move it up or down. And you may remember from an earlier chapter, there's a phrase about how graphs get transformed. It says add to x, go left, and add to y, go high. So if you look at this graph, how did we transform it? So let's say this purple function is the original function. That's y equals radical x. That's the parent function. What does this function look like? Well, we're adding to x, so that means we're going left. We're going left 4. So 1, 2, 3, 4. There's what that x plus 4 graph looks like. It's the same as the parent function. It's just been shifted to the right 4. And you can see that it's still not going up or down at all. It's still, y is still going to be everything that's up here in the positive. So y is greater than or equal to 0 would be the range. The only time the range changes is we'll see an example in just a sec. It's when you start moving that graph up or down. We didn't move that up or down, we moved it to the left 4. That's what x plus 4 does. Alright, let's do a couple more. So let's say this is x minus 3, and for all of these I'm going to start by drawing the parent function, just so that we can have that in front of us as a picture, so we can see what that looks like. So that again is y equals radical x. And then let's transform these. So this one, what is this going to do? This is add to x, go left. So in this case we are subtracting from x, so this means we're going to go right instead of left, and we will go right 3. So I'm going to take this graph and I'm going to go 1, 2, 3 to the right. So there's my new picture. What's the range of this, or sorry, what's the domain of this? Well, it's nice to have the graph because you just see x can't be anything over here. So x is only stuff in this zone right here, and that is x's that are greater than or equal to 3. So there's your domain. Another way you could have done that is to set x minus 3 equal to 0. And when you solve that, you'll get x equals 3. So you look at it and you say, well, what side of x equals 3 would cause problems? And the side that would cause problems is if x were less than 3. If you plugged in a number less than 3 right there, you'd have the square root of a negative. And you can't do that. Okay, what's the range? The range is still the same. We didn't, if you look at this x minus 3, we didn't move it up or down. We just moved it right. So we still can't go anywhere down here where y is negative. So that means y is greater than or equal to 0. Y is anything that's 0 or above. Okay, what does this one do? Well, the plus 6 makes it go right 6. And then remember, it also, besides add to x, go left, we say add to y, go high. So this right here, this number, is making it go up 2. Add to y, we're adding 2, so we're going high. So how can we do this? Well, we can start by taking the green and shifting it to the right 6. So that right there, that's 6 points to the right 6, and then we're going to move it up 2. So that is where the graph now starts, and it looks the same as the green one. It's just been shifted right 6 up 2. So that's going to change the domain. Okay, the domain is going to be, well, this right here is x equals 6, and you can see x can be anything this direction. So anything that is greater than or equal to 6 would work for x. The range has now changed also. Notice that y equals 2 right here, the graph never goes below. That's the purple graph, it never goes below y equals 2. So that means y must be greater than or equal to 2. And that comes from that plus 2, the fact that we added 2. Alright, this is just a summary of what we just said, the different ways that you can transform. So this number here tells you whether you're going right or left. This number here tells you whether you're going up or down. Add to y, if it's a positive number, you go high. If it's a negative number, you go down. Okay, and then the a does two things. The a, first of all, if the a is negative, that means you flip it. And we saw this with parabolas, like y equals negative x squared. That's an upside down parabola. So negative means you flip it over the x-axis. And then if a is greater than 1, you will vertically stretch it, which means you horizontally shrink it. And if a is between 0 and 1, so if it's like a fraction, you would vertically shrink it or compress it, and that means horizontally expand. Vertical and horizontal do opposite things to each other. If you let's say you have like a slinky or something, I'm not going to draw a very good picture here, but let's say you have this rolled up slinky and all of a sudden you vertically stretch it out. That means horizontally it's going to be kind of stretched inward. It's going to compress or shrink, and vice versa. If you have something that's really tall like this, you have some sort of box or something and you crush it down, that means horizontally it's going to be crushed in. It's going to kind of expand outwards. Sorry, I wrote that wrong. Actually, it's supposed to go this way, outwards. Alright, so let's graph this right here. And the easiest way to do it is by finding the center point. And the center point means setting this equal to 0. So we want that to equal 0, which means if we add 2 to both sides, x will be 2. That's where our graph will start. So we start by making it equal to 0, the inside of the function, because important things happen to a function when it equals 0. Alright, when x equals 2, if we plug it in, we'd have square root of 0, because 2 minus 2 is 0, so square root of 0 plus 5, and that would just be 5. And then really you only need 2 or 3 points, so let's just add a couple more. In terms of what points we want to add points that are going to make these numbers show up, perfect squares. So we want x minus 2 to equal 1, we want x minus 2 to equal 4, want x minus 2 to equal 9. Why do we want those numbers to show up? Because we're taking the square root of them, and it's easy to take the square roots of these numbers. We wouldn't want to make it like 2 or 3 because those are not perfect squares. Okay, so x minus 2 equals 1. When is that going to happen? That's going to happen when x equals 3. So that's going to go in my table. When will x minus 2 equal 4? That's going to happen when x equals 6. And let's just add one more. That's going to happen when x equals 11. So let's just add 3 and 6. That's good enough. Notice it doesn't have to go up by 1 each time. It's fine if we skip around. So if we plug in 3 right here, 3 minus 2 is 1. Square root of 1 is 1. Plus 5 would be 6. And then if we plug in 6, the square root of 6 minus 2, that's the square root of 4, which is 2. 2 plus 5 is 7. So we can graph these points, but here's another way that you could have done that. Okay, I'm going to graph the parent function, which is y equals x, and it looks like this. Okay, that is, sorry, y equals radical x. That looks like that function. We could also graph it using those points we just did, or we could do the transformation. So what does minus 2 do? It moves it right 2. And what does that do? It moves it up 5. Add to y, go high. So let's just take our purple graph and move it right 2. So this point is going to move to the right 2, and then it's going to move up 5. So we'll start there. And what's that point? That's the point 2 comma 5, which we had right here. I'm just showing you a second way to do this. Okay, then the second point we had in the graph was 1, 1. That's going to go right 2, so it's going to be here at 3. And it's going to go up to 6. So 3, 6, and that point is right here. Finally, we had this point on the purple graph. We're going to move it right 2, and then we'll move it up 5, and that's the point 6 comma 7, which is also right here. So you can graph these two ways. You can graph them using table of values like you see on the left, or you can do it with transformations like we just did right there, going all those points on the purple and moving them right 2 and up 5. What's the domain in the range? The domain is any x that is, let's use a different color so you can see it, any x value that is to the right of that dot, and that dot occurs at x equals 2. So that means x can be greater than or equal to 2. What's the range? The range is any y value that's above that 5 right there. So y is greater than or equal to 5 would be your range. Alright, this one's a little bit different. We don't want to do this by transformations because we have that negative 2 sitting in front. And even though it's easy to see what right 3 looks like and what down 1 looks like, because that's what the plus 3 and the minus 1 do. Sorry, that's not supposed to be right 3. That should be left 3, because add to x, go left. It's not going to be easy to see what this stuff does. So the minus, you might remember, the minus is going to flip it over the x. And the 2 is going to either vertically stretch or shrink. And because 2 is, you're doubling something, that means you're making it bigger. You're vertically stretching. If that were like 1/2, like something like a fraction, that would mean you're vertically compressing or shrinking, which would be horizontally expanding. So in purple, I'm going to do our parent function again, just so we can see how the transformations look. But again, this is not a good idea to try to move it around, because it's not going to be easy visually to tell. What does it look like to vertically stretch by 2? That's not really easy to do just by sight. So let's make a table of values again. And 3 points should be enough. And again, we want these numbers to get plugged into the function. And actually, let's start with 0. So how would I make the radical 0? I could make it 0 with negative 3. And then let's solve that out. So we have negative 2 times negative 3 plus 3 minus 1. This whole thing will be 0 minus 1 is negative 1. So we have a point at negative 3 comma negative 1, which is right there. Okay, next point that we want to get plugged in, we want 1 to get plugged in. So how can I make this thing equal 1? I can make that equal 1 when x is equal to negative 2. In other words, if I plug in negative 2 right there, negative 2 plus 3 would be equal to 1. Why am I picking 1? Because 1 is a perfect square. So let's plug that in. So we're going to have negative 2 times, now I'm plugging in negative 2 plus 3. Negative 2 plus 3 is 1. The square root of 1 is is 1. Times the negative 2 would be negative 2. And then negative 2 minus 3 would be, sorry, negative 2 minus 1 would be negative 3. Okay, last one, we want to get 4 being plugged into the square root. So I need the x plus 3, the thing under the square root, to equal 4. When does that equal 4? It equals 4 when x equals 1. So I'm going to put 1 right here. And then let's use that and find what the y is going to be. I'm plugging in a 1 there because that's where the x goes. When you solve that out, you'll get the square root of 1 plus 3, that's the square root of 4, which is 2. 2 times that negative 2 is negative 4. Negative 4 minus that 1 is negative 5. So let's graph these other 2 points. Negative 2, negative 3 is right here. And 1, negative 5 is right here. So notice what happens when we connect the dots here. Let's just make sure we did this correctly. Just double checking here. Negative 4 minus 1 is negative 5. Negative 2 minus 1 is negative 3. Yeah, so that should be right. Okay, so notice this was supposed to have been flipped over the x-axis. So if you, I'm going to draw this a little different. If you flip this over the x-axis, it's going to look like that red line. And then you're going to move it left 3, so you can see there we're moving it left 3. And then we moved it down 1. It normally would be up here, but we moved it down 1. So that seems to agree with the picture. And then you're vertically stretching it. So this is going to kind of look stretched out. It looks like that. You can see the red looks like the purple. It's been flipped over the x-axis, and it's been kind of stretched out by a factor of 2. So that seems to agree with what we have. Alright, last couple things I want to show you. So I'm going to show you a word problem first. Okay, with those types of problems, and these are ones used in real life. There's plenty of natural scenarios where you have word problems. This example is with hertz. That's a unit for sound, and they're talking about, I think, a violin or guitar string. The frequency or the pitch of a string is modeled by this function right here. T stands for the tension, and instead of T, we'll just replace that with the letter X when we're graphing. So obviously you'd want to use a graphing calculator for this. I'm going to plug that in. 1 over 1.28. So let's do that. So I'm going to put that in parentheses, because if you don't, the calculator will cause problems with order of operations. And then we have the square root of x over that huge number. So second square root, and then we have x, and then we're going to divide by what? By point, it looks like there are 4 zeros. Point quadruple 0708. So point 0.0000708. Let's zoom standard to see if we get a good picture. And we don't, so let's change that to zoom fit. And that's a decent picture. It's not great. We can always zoom out if we need to. So we're being asked to graph the function. We did. And here's their picture. It's a little bit better. It looks like the window there is, maybe we can just expand the window a little bit. So let's go to window. X is going from negative 10 to 10. Let's make the y max higher. Let's make it 400. And let's increase by 40s instead of by 10s. Okay, that's a little bit better picture. So graph the function. We did that. Then it says how much tension for a pitch of over 200. So that means when y is more than 200. So how do we do that? We go to second calc, and we want to find an intersection, basically. Let's try this. Yeah, we don't know what the x is. We want to find an intersection. And what do we want it to intersect with? We need to intersect with when y equals 200. And why is that? Because they're asking us for a tension of over 200 hertz, but remember in this equation, this value, which is y, that is tension. Yeah, sorry, that's hertz, that's Hz. So y equals 200. So all I did there was I graphed a line y equals 200, and then you can see there's two curves there. We want to know when they intersect. So we go to second calc intersect. Okay, this is our first curve, so you just need to be on the curve, which I am, and press enter. Now you can see it's blinking on the blue curve. So I press enter, and then guess. You can just go close to the intersection, and it tells you at 4.64 for x. So at 4.64 kilograms, that is when we intersect. And you can kind of see that on the graph. That right there, if you follow it down, that's somewhere between 4 and 5. So it's 4.64. Alright, we'll finish up with this inequality right here. How do you graph inequalities? It's really the same as graphing equations. You just need a solid or a dotted line. Okay, so this is going to move the graph right 4 and down 6. So let me draw the parent function first in blue. Parent function looks like this from before. Here's the parent function. We're just going to move that to the right 4 and down 6, because add to x, go left, we're subtracting from x. So let's move the right 4 down 6. So there's the first point. That's this original point. If we move this one right 4, it goes to x equals 5. Down 6 would take it here. And then if we move this one to the right 4, we would get to 8. And if we go down 6 from 2, we would get to negative 4. This should be a dotted line because that's not greater than equal to, that's just less than. So we're going to make a dotted line. And then it says y is less than that. So if you want to shade less than, you would shade down below like that. That is exactly how that graph will look. It has an inequality, so again it's a solid line. And why are we shading below? Because it says y is less than that. Okay, so that's what it looks like. So that's how to graph square root functions in section 6.3.